Okay, here's our last question for the data analysis practice. We've got electrical resistance. It's a question about electrical resistance. The resistance of a sample was measured as a function of temperature. As a function of means temperature is on the x-axis. Okay. The sample was cooled and the data points were taken at temperature intervals. Like this. It was cooled and the data points were taken at temperature intervals of 0.2. So we started out hot and we cooled it, and every 0.2 Kelvin we recorded the resistance. So you can see some gaps between the data points, right? Ooh, interesting. The uncertainties in R and in T are too small to be shown on the graph. That means, right, if the uncertainties are too small, you know you're looking at the true values. These are not just measurements. These we can assume are the true values. And the reason is because the uncertainties are so small. The uncertainty, remember, encompasses all random error and all systematic error. And so the true values must lie within the error bars. So you're looking at the true values right here because the uncertainties are virtually zero. The hypothesis is resistance is proportional to absolute temperature. That's another term for the Kelvin temperature. For temperatures greater than 4.5 Kelvin. Here's 4.5 Kelvin. So higher than this, temperatures higher, so on the right half, they're saying, does the data support that R, resistance, is proportional to T? Clearly not. This is not a straight line, right? This does not make a straight line. If you try to draw a straight line, then you're not going to pass through all of the error bars, which are really just, you're not going to pass through all the data points because the error bars are so small. So whether or not, no, the data doesn't support the hypothesis. Why not? So now let's say, so we've said whether, now let's explain. Suggest means also explain. And because the graph, we could just say isn't straight at temperatures bigger than 4.5 Kelvin. State the value of R for which the rate of change of resistance of the sample with temperature is least. Okay, a hint. The rate of change of Y with X is another way of saying the slope or gradient. Rate of change of Y with X is equal to slope. Resistance, rate of change of Y with X. They're saying find the value of R, right, somewhere along here. Which value of R is it where the slope is smallest? Let's see. Well, here the slope is 0, and then the slope is like that, and the slope gradually increases. So at what value of R, where on the y-axis, do we have the smallest slope? Right here, right at the very beginning, at R equals 0. Slope is a minimum. It's 0. Use the graph, okay, at a temperature Tc, the resistance suddenly becomes 0. So you're cooling, gets smaller and smaller temperatures, and then bam, you drop to 0. Right? Suddenly drops. Use the graph to determine the possible range of temperatures, the possible range of this sudden drop, temperature of sudden drop. Well, look at this. Here's where it could drop right there, or it could continue on and drop right here. So this is the range of temperatures. What is that? We're going where you have 0.5 divided by 1, 2, 3, 4, 5. Each little tick mark, the little tick marks are all 0.1. So we're at 4.5. 4.4 is the maximum TC max is 4.4 Kelvin, and what's TC minimum? Let's see, the minimum, it could drop right here. It could continue and then drop, and that'd be 4.1, 4.2. So the range is from 4.2 to 4.4 Kelvin. State to the correct number of sig figs the value of TC and its uncertainty. Oh, this is a range. So they want you to say the likely value is halfway between, right? Or at least the central value. Do max minus min over 2. And you do 4.4 minus 4.2 over 2. That's going to be 0.2 over 2, or 0.1. That's the uncertainty in TC. Right? The way that you find the uncertainty when you have max and min is you take the difference, divide by 2. Is that what I said earlier? That's how you find the uncertainty. And now, so the central value is found differently. The central value is max plus min over 2. I think I said central value, and then I wrote the equation for uncertainty. So take the central value, just average these together, and it's 4.3. So state with correct sig figs the value and its uncertainty. The answer is TC equals 4.3 plus or minus 0.1 Kelvin. Right? And look, if you add 0.1, you get to the maximum. If you subtract 0.1, you get to the minimum. Outline how TC could be measured more precisely. I'm going to let you look at the answers for this, but it involves things like, measure smaller than every 0.2 Kelvin. Measure R more frequently than every 0.2 Kelvin. That's one good one. I mean, if these data points, if you have a data point here, and a data point here, and a data point here, then you'll know exactly where it drops, or at least you'll have a closer, a more precise estimate. So just measure values of temperature measure values of resistance more frequently than every 0.2. Right? So get what the resistance, what's the Y value right here, and all these smaller subdivisions. Outline 2 reasons why you couldn't use the data to determine an accurate value for R at room temperature. Why can't you get an accurate value of R at room temperature? We haven't learned this, but room temperature is around 300 or even higher Kelvin. Okay? We're looking at 7 degrees Kelvin. I mean, 300 is like way off the graph. So we already saw one change in the trend. The mathematical trend changed after just from 4 to this range. In the span of, here's how I say it, in the span of 7 Kelvin, we saw the trend change once. Did I draw a best fit line? Uh-oh. Here's my best fit line. I should go through all the data points. Uh-oh. I should have gone through all the data points. Well, I missed that. Don't miss the questions, right? That's easy to do. Don't miss it. You don't need to connect these two trends to get the points. Right. So within the span from 2 to 7 Kelvin, the trend changed once. We have no idea what's going to happen as we increase another 300 Kelvin. How many more times could the trend change? We just don't know. So that's what you're going to describe. Right? The trend already changed once in the span of 2 to 7 Kelvin, and 300 is much, much, much higher than any of the data, so we cannot extrapolate that high.